Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, integer to English words. And I really like this problem because it reminds you to ask yourself, what's the meaning of life? And the answer, of course, is to suffer. Jokes aside, this problem is very tedious, but there actually is something that you can learn from it, like just kind of taking a problem, making some observations and breaking it down. I'll kind of show you the thought process I went through. But if you don't like this problem, I actually did a little bit of Scooby-Doo analysis and went to the old version of Leetcode where you can see that this is quite a disliked problem because it's pretty tedious. Before I get into it, I kind of want to just show you my process of solving the problem. So I came up with my own solution. It took me about 38 minutes. Here, as you can see, the problem came out at 5 p.m. Pacific time. And so 38 minutes later, and some failed attempts because I did miss a few edge cases, this is the solution I was able to come up with, which technically works. You can see this is the tedious part, this mapping. I missed this edge case, but this is kind of the solution I came up with. There is a shorter solution. After this solution, I was kind of able to realize that this is some repeated work, and also skimmed through the editorial. By the way, these are the observations I made to solve the problem. But a few minutes after that, I think you can see 8 minutes after that, I was able to slightly optimize the solution by creating a loop. And also then this helper function that I was using, I was able to kind of make that a little bit more readable a few minutes later as well. Here you can see, well, not that much more readable, but anyways, this is kind of the final solution that I'll be showing you, but I'll still be walking you through the thought process that I went through. So the idea is pretty simple. We're given a non-negative integer. Thankfully, it's non-negative, but it could still technically be 0, and it will be up to 32 bits. So it could be up until, I think, 2 to the power of 31 minus 1. The reason it's 31 is because we're not dealing with negative numbers, so we're only using 31 of the bits. It's going to be up to a big number. So in terms of 32 bits, it can contain, the max value is something like 2 billion, 2.1 billion, something. So just to kind of draw out how that looks, this is kind of the max that we'll be dealing with. So we're never going to have 3 billion or anything larger than that. This is important because when you start to just make a lot of observations about numbers, just start counting, we have 1, we have 2, we have 3, and we can kind of do this all the way up until we get to the teens. We get to 10 and 11, and this is the tedious part. We go all the way up until 19. So all of the first 19 numbers, and I guess you could count 0 as well, all of those numbers are going to have a separate string for each of them. But after that is when we start to see some repeated work. So not quite yet, but when you get to 20, this is the first part where we're going to see some repeated work, because now we have 20 and then we have 21. So this is a repeated thing. This number is 21. This part is repeated. This is the 20. And it keeps going like that. So we have 30 as well. And we can go all the way up until 90. So make sure you don't have typos when you make these words, because believe it or not, I thought this number 40 is written like this, 40, but no, it's actually written like that. So that was another reason I failed one of the test cases. Once you kind of recognize that, now we can start to break this problem down into repeated work. So we have the 10s and 20s. That's actually all we need. We will need the strings hard-coded from 1 through 19. We will also need the strings hard-coded from 20 to 30 all the way up until 90. So I'm not drawing all of them, but those are the hard-coded strings. So it's about 30 hard-coded strings. Once you have all of those, you can actually solve the problem for the most part. So if we have 2-digit numbers, we will be able to convert that into a string, because either it's less than the value 20. Sorry, I'm writing it wrong. If it's less than 20, then we can just look it up here in this set of strings. If it's greater than or equal to 20, that's when things get a little bit interesting, because if it's 20 itself, then it's just going to be the string 20. So we can kind of look that up as well. But suppose it's 21. Well, then we have to take this part, look it up, and then we have to take this part and look it up. We know we don't have to look up the second portion is if it's 0. If something is 0, we kind of don't have to say it's 20, 0. So that's why we ignore the 0. That's another thing to notice, because we're going to be ignoring zeros in other places as well. Now, if it's 37, for example, again, you'll have to look up this and you'll have to look up that. If it was 30 though, you don't look it up. Same with 20. So that's repeated from 40 all the way up until 99. After that though, things get interesting once again when we add another digit, 100. Good thing about this though is that this number, for example, is written as 100, and then you take the last two digits and it's just a subproblem, right? So you'd look up this digit and you'd look up that digit as well. That's the only thing that's going to be different here. So whether this is a 1 or it's a 9 or anything in between, we're going to take this number and look it up in this set. And that'll tell us the word to put before the word 100. So now with 4 digits though, it gets even more interesting. So I'm just kind of running through these. We're almost done, believe it or not. There's just a few more patterns to recognize. With 1,000, let's say we have 1,234. How would you break this down? Well, this is going to tell us how many thousands we have. So you would look this up over here. At least that's what it seems. And then this would just be what I showed you earlier. So like 1,200 and then 34. So this is like, you look it up however. But what if we had something like this, 1,034? You skip the hundreds. So something we're going to have to account for. Now, this is the part where everything is going to start repeating. You're going to notice that you only need to pay attention to 3 digits at a time. Now, I'm going to write out a big integer just because I want to save time. We don't need to go through every literal example. Let's do 2,123,456,789. This is one subproblem. We kind of realized how we can solve this. You look up the hundreds. That's going to be in the ones place. And then you just break this down. You get the tens. Well, the tens is over there. And then you get the ones over there. So you break that down. Some of them could be 0. That's perfectly fine. Now, this tells us how many thousands we have, but it's similar to this. Like this is 789. We could have had a 789 over here. The only difference is that that would have the word thousand right after it. So as you can kind of see over here, we have 12,000. It could be that this is just like a digit of 1, like these could have been zeros and this could have been 6,000, or it could have been 16,000, or it could have been 456,000. Again, it's repeated work, just that we add the word thousand after it. This is the exact same. This tells us how many millions we have, but we break it up into 3 digits. So it's 123 million. This could have been all zeros. What would we do if it was all zeros? Well, we have 0 million. So we don't really need to explicitly state that. If this is all zeros, we can consider it to be an empty string. And lastly, this here is going to be pretty simple, but we can solve it the same way we solved these. We can kind of just assume that there's a couple leading zeros or whatever, but this is 2 billion. We would just do a lookup and then just add the word billion after it. So I think conceptually, this problem isn't crazy, but no matter what you realize, it's kind of a pain to code up. So I think at this point we can get into the problem. In terms of analyzing the time complexity, it's pretty interesting. I mean, given that we know we're not going to be dealing with numbers that have more than 10 digits, technically you could say it's constant time and constant space. I think our solution is going to be constant space at the very least, but suppose we actually had an integer that is unbounded. Like it could be infinitely large. Like in Python, you can have integers with arbitrary length. The way we're going to be dealing with this, as you might guess, we're going to be doing a lot of math to extract integers 3 at a time. Suppose roughly we divide this by 10 to get each integer, or we mod it by 10 to get each integer. So it's basically a matter of how many digits are in this problem. Again, this time it's roughly 10, so it's constant, but suppose it was arbitrarily long. What would we say is the time complexity in that case? Well, if n is the number of digits, you could say the time complexity is big O of n. But suppose n does not represent the number of digits. Suppose it actually represents the integer itself. Let's say this is n. How would you describe the time complexity then? Well, given an integer that is like represented in base 10, how would you get the number of digits of it? Well, you basically ask yourself, how many times could you divide this number by 10 until it reaches 0? So that's basically log base 10 of n. So that's kind of similar to like binary. If you had a 32-bit integer, you'd say how many times can you divide it by 2 until it's 0, and it's going to be 32 because there's 32 bits. At least that's like the worst case. So this is very much a math problem, but there are some problem solving components to it. So now let's get into the fun part, writing out the code. One base case about this problem is the number could be 0 itself, and then our algorithm doesn't really apply because remember, we're going to be ignoring 0. So I'm just going to add this if statement here. And the only reason I knew to add this was because I submitted my code without really thinking about it, and I got this test case which failed. So that's one thing. Now, the second thing I'm going to be doing, this is kind of stylistic. You can do it differently if you want to, but here I'm going to have a couple hash maps, and I mean, there's probably a better way to write them, but I think this is relatively readable. I'm going to have two maps. One is the ones map, because like I said, we're going to need to hard code the strings for 1 through 19. So that's pretty much what I'm doing. And the second map is the tens. So 20 through 90, those are also hard coded. Those are pretty much the only hard coded strings we're going to need other than hundreds, millions, and thousands. So I'm going to get into the general structure of how I'm going to code this up. So I'm going to have a helper function, and I'm just going to call it getString. There's probably a better name for it, but it's going to take an integer. Let's call it n. And n is only going to be up to 3 digits. Because remember, we're going to be processing the input 3 digits at a time. And so let's expect that this is going to return the string. It's going to convert those 3 digits into a string. Suppose we have something like that. How would you structure the rest of your code? Well, this is what I would do. We're going to go through nums. While num is not 0, we're going to get 3 digits at a time. So I want to get the last 3 digits. That's easy to do. Just take num, mod it by 1,000. So divide it by 1,000 and get the remainder. So everything smaller than 1,000 will be left over, and that's what digits will be. And then at some point, we want to do this. We want to obviously call getString on the digits, and then we'll have that string. And then we want to take our digits, and then on the next iteration of the loop, we want the next 3 digits. So we can remove digits from this number by dividing it by 1,000. So I'm going to say num is going to be equal to num divided by 1,000. The reason this works is suppose you had something like that. If you were to take this and divide it by 1,000, you'd say, you know, we have this many thousands. So this is dividing by 1,000 and rounding it down. So it would just remove these 3 digits over here and we'd be left with this. That's how many thousands we had. The interesting thing about this is that we need like a string after it. I'm going to call that the postfix. I don't know if that's the best name for it, but that's what I'm going to call it. First time it's going to be empty. The next time it's going to be 1,000. The next time it's going to be 1,000,000 and then 1,000,000,000. So we're going to have an I pointer, which tells us where we're at in terms of that. And so here to the string, after we call this, let's add the postfix after it. So I'm going to do postfix of I. And you got to be very, very careful. Like a white space will mess up your solution. So suppose this returned like 34,000. Well, when we concatenate that, we want to add a space between these two. And the easiest thing to do is just add a space here, here, and here. So the way I'm going to code this up and return my result is not by building an entire string. Actually, it's probably easier to do that, so I guess I will. I mean, I was going to do it like this by making result an array and then just joining all the strings in array. But the thing is that clearly we're going to be getting the hundreds or the ones first, and then we're going to be getting the thousands, and then the millions, and then the billions. So we're kind of doing it in reverse order. Like when the number is actually written out, we first start with like 5 billion, this many million, 300 million, and then 2,000 or whatever. So I guess it might be easier to just start result out as an array. And when you have this string here, we can just add to this. But actually, now that I think of it, each of these parts needs to be separated by a space as well. So I guess I'll actually just stick with doing it as an array. So now I'm going to do that. I'm going to have returning this. At the end, I want to join all of the parts, separating them by a space. I can do that like this. So dot join everything in result. So now we just got to make sure that when we take these strings and add them to the result, we do so in the correct order. So it's technically possible that this function could actually return an empty string. Suppose we were given something like this, 1,000,000, all zeros, and then all zeros here. For the first part, this is going to return an empty string because there's nothing there. For the next part, it's also going to return an empty string. We don't want to add those empty strings to our result because then if we join them, we're going to mess up the white spacing. I only know that because that's like an issue I ran into as well when I submitted this. So I'm going to add an if statement here. Make sure that this is not an empty string. And if that's the case, then let's add it to the result. But we're going to do it like this. We want to add it to the beginning of the result. So in Python, that's pretty easy to do. We can just create an empty list here, which is just S, and add that here. We don't really have to worry about the time complexity of this operation because this list should never grow beyond the length of 4. And if it did, I guess we could just do this result dot append the string, and then at the end we could reverse it. So, maybe I'll just do that here, reverse this. But anyways, I think we're getting too much into the weeds. So we're pretty much almost done with this core part. Just don't forget to increment your I pointer. So I'll do that here. This bottom part is pretty much done. So honestly, if you were able to do all of this in a coding interview, I would easily pass you because this is not an easy problem to break down. I would definitely not ask you to hard code these. I think in most interviews, your interviewer wouldn't want you to do that. Like they get bored of watching you type that out. So I think in a real interview, you'd save a lot of time doing that. But they might want you to implement this function, which personally, I wouldn't mind if you missed a few edge cases. And I think most interviewers wouldn't. They'd probably give you some hints as well. So let's get into this. We're going to be kind of implementing the digits the same way we did here. We're going to do a list like this, and then right at the end, we're going to join them by adding a space in between all of them. We want to extract 3 parts from this. Suppose we have an integer like this, 123. We want to get the 100. How many hundreds do we have? And then we want to get the 23 part. Remember, it could also be something like this, 120, where we have a 20, but this isn't really like represented since it's 0, or we could have something like this, 102, where we don't have any 10s, but we do have this. We'd also, of course, have no hundreds. We could have 12, for example. So we got to account for all of these, and it's not too difficult to do, but it's very easy to miss a lot of edge cases here. So first, let's get how many hundreds we have. We can just do that by dividing by 100. We can take n and do integer division by 100. Now, let's check that this is non-zero. So if hundreds is non-zero, then to the result, let's append how many hundreds we have. Well, we need to do that in terms of strings. So how do we get that string? Well, how many hundreds we have is going to be 1 through 9. So we can use the ones map. That's why we have it. So append to this, the ones map from hundreds. And actually this string, we want it to be a single string. So before we append it, we want to add to it at the end how many hundreds there are. So this is going to be one string before we append it. Keep that in mind. We don't want to append 2 separate strings with these words. I guess we technically could actually if we got rid of the space here, but this is fine as well. So now we want the last 2 digits. So I'm just going to call that last 2. I'm going to take n and mod it by 100. It's possible that it was less than 100 to begin with, in which case the mod will still give us the last 2 digits. So now there's a couple cases. Remember, if the last 2 digits is less than 20, we can just do a very simple lookup. But if it's greater than or equal to 20, it involves a bit more work. So I'm going to have a conditional for that. If last 2 is greater than or equal to 20, that's when we have extra work. If it's not, then we have some simple work. But the reason here I have an else if is because of this. What if this was 0? Well, that's a case that we actually missed over here. We could have 100 and nothing's here. So we want to make sure it's non-zero, because if it's 0, there's no need to append anything anymore. So here, if it's non-zero, that's the simple case, then we will append whatever value it maps to. It's less than 20, so we can just use the ones map like this. Map the last 2 to the word and then append it to the result. So that is done. Now for this interesting part. Here, we might need both the 10s and the ones. We know the value is greater than 20, so we're obviously going to have something in the 10s place. So let's get both the 10s and the ones. We can do a bit of math. Last 2 divided by 10 will give us how many 10s we have. Last 2 modded by 10 will give us how many ones we have. And then we want to append to the result how many 10s we have. 10s, though, is a single digit right now. So like, let's say we have 123. 10s is going to be 2. So to look up in the 10s map, we're going to multiply that number by 10, or we could have probably just not had the zeros here, but whatever, I guess it doesn't matter that much. But here we're going to take 10s, multiply it by 10, and then use that in the tens map to look up the string. So like this. Now, ones could still be 0 or it could be non-zero. So that's why we'll add another if statement here. If ones is non-zero, then we will append to the result, looking up in the ones map, whatever ones happens to be. So that's pretty much it. I might have a bug though. It's very easy to have a bug in this problem. Hopefully I don't. I will kind of just slowly show you all of the code. This is kind of the main part of the code. This is another main part. You can see we actually did most of it in less than 30 lines. It looks like about 26 lines of code if you don't include these massive hash maps. And also, I guess, the if statement up here. Let's give this a run though. Okay, so we did have a mistake. Let's see where that mistake is. Let's just do a quick bit of debugging. It looks like we had the string 1,000 when we didn't need to, even though these were all zeros. Let's see if we can find the bug. Okay, so I see the problem. Here, we're adding the postfix to the string, but it's possible that the string was empty to begin with. So it looks like our if statement here is always going to be true. Why do we even have the if statement? It looks like we're always appending the postfix. I guess on the first iteration, it might still be an empty string, but we should probably just move this postfix inside here. So that's what I'm going to do. Boom. And then here, I'm going to append to the string before we append it to the result, just like this. So hopefully this fixes the bug. And it looks like it did. This time, the runtime doesn't seem super efficient, but you can see that when I did the submissions, it varied quite a lot. Like we got down to 31 milliseconds with pretty much the same solution. That was very efficient, so don't pay too much attention to these. I hope you found this helpful. Even though this problem is really tedious, there is still a decent amount that you can learn from it. Thanks for watching, and I'll see you soon.